everybody. Today we're going to finish up our linear kinematics notes. We only have one more thing to look at. So we've looked now at a formula for constant velocity. We've looked at the definition of acceleration. And last time we looked at the general equation for linear motion. Now, what we need to remember is that all three of those formulas are time dependent. You have to know the time in order to use them. So that presents a problem. What if you don't know the time and there's no way to find it? Scientists understood that this would be a problem. If you don't have the time, there's no way to find it. What in the world are you going to do? Well, they realized, since this was a problem, they needed to come up with a formula that would do the same thing as the general equation, but it would be time independent. In other words, it's not a function of time at all. There's no time in the formula, so that if you don't know the time, it doesn't matter. It's not in the formula anyway. So here's what they did, guys. I'm going to show you. You don't have to know this. It's just kind of a cool little thing to see. Here's what they did. They started with the definition of acceleration. All right, there it is. And they rearranged it to get an expression for time. There it is. If you do numerator denominator switch, you get d equals vf minus v sub I over a. All right, then they took this expression for t, and guess what they did with it? They shoved it into the general equation. Ooh, look at that. All right, and then they started combining terms, cleaning things up, and ooh, look up here in the numerator. You're going to have to do the FOIL method. If you have vf minus v sub I squared, you're going to have to FOIL it, and then you're going to have this a, and you got an a in the top, a squared in the bottom. One cancels, one doesn't, and okay, so you got all this stuff. Well, they keep working with it, and after a while, stuff starts falling out. You've got a positive to this and a negative to that, and stuff like that. So it drops out. And here is what they were left with. They were left with this right here. And this is what today's lesson is about. It is called the alternate equation for linear motion. Now, let's put it on our paper, okay? We're going to put this formula on our paper right here in this big spot. So, the alternate equation, it's final velocity squared minus initial velocity squared equals 2 times the acceleration times the displacement, okay? And this is what we call the time-independent formula, or, if you will, the alternate equation. Now, why alternate? Well, because it's our alternative that we can use when time is unknown. But you will also hear people call it the time independent equation too. Because it is. It's independent of time. Don't need to know the time. Okay? Now, let's see how we're going to use this one. Right here we have a race car that decelerates by 5.7 meters per second each second uniformly, so uniform deceleration, to a stop. If the race car was traveling at 85.5 meters per second originally, how far is the braking distance? Okay, so the focus object obviously is this race car. Now, what are we given? We are given, oh look, the deceleration rate. So A equals, and if we take the forward motion of the car to be positive, then our deceleration will be negative. We'll subtract it from our velocity. So there's the deceleration. Here's another numerical piece of information. 85.5 meters per second. Now what is that? Well, it says the car was traveling at this velocity. Meters per second is velocity. So if it was doing that, but it's not now, this must have been the initial. So 85, and that we'll take that to be the positive direction, 85.5 meters per second. Now, I don't see any more numbers. Okay, so we've gotten all the numerical information identified correctly. Now let's go to the inferred information. And as far as I can see, there's only one thing that's inferred, and this is it right here. The car eventually stops, which means the final velocity is a big fat 0. Okay? I can't tell anything else from that. All right, so what are we trying to find? We want to find the braking distance. We want D. Notice, of everything we know and what we're trying to find, there's no time. There's no time known here. So, when there's no time, we're going to use the alternate equation, all right? Now, I'm going to rewrite it backwards. I'm going to put this side on the right and this side on the left, all right? Because we want to find D. So I'm going to say 2AD equals V sub F squared minus V sub O squared, okay? Now, we know the car comes to a stop. So that is going to drop out. 0 times 0 is 0. So we're left with 2AD equals negative V sub O squared. We're solving for the D. We're multiplying it by 2A to get the 2A to the other side. We simply divide. Okay? So there's our working formula now. We plug and chug next. So we get minus the quantity 85.5 meters per second squared. Now notice we're squaring the 85.5, not the minus sign. This is a term squared minus another term squared. It's the difference between two squares, okay? So you're not squaring the minus sign, but that's okay because look right down here. When we put in the acceleration, look what we have. So what happens here? Oh, look. Here's what happens. That one cancels with the one on the bottom because a negative divided by a negative is a positive. All right, unit analysis. Let's take a look. We get second squared. So the seconds are going to cancel out. We get meter squared on top divided by meter on bottom. So this meter cancels with one of those two and leaves 1 meter behind, which is a good thing because we're measuring displacement and it's measured in meters. So take 85.5 and square it and divide by, what would that be, 11.4? So 85.5 squared divided by 11.4, and you should get about 641 meters. And double check me on that, okay? Now, so was that terribly difficult? I don't think so. I think the hardest part most people have is correctly identifying the information. But guys, it takes practice and it takes knowing what your units measure. All right, meters per second squared is an acceleration. Meters per second is a speed or velocity. You've got to know your units. If you don't know your units, you won't be able to identify anything correctly. And you'll never get the right answer. Okay, let's look at another example real quick. We have a ball dropped from a height of 15 meters. How fast is it moving when it reaches the ground? Okay, let's take a look. We're going to drop a ball. Here's, balls are round, duh. We're going to drop it down to the ground, okay? How fast is it moving when it reaches the ground? So we want to find the final velocity just as it strikes the ground. And we're not talking about after the ground decelerates it to a stop. That's a completely different motion. Remember, it's only in free fall while no other forces are acting on it. Once it strikes the ground and the ground exerts an upward force to slow it to a stop, that's a completely different motion from the free fall. So we're not concerned with that. We're only concerned with the free fall. And we know the ball does strike the ground and it will be moving at some velocity when it strikes the ground, and that's what we're trying to find. So let's start with what's given. 15 meters, that's the distance that it falls. Okay, so it goes from here to here, so this is D, 15 meters, okay? And notice that's the only That is the only given piece of numerical information there is. So we must have some inferred information. Here we go. Let's find it. All right. First off, we know the ball is in free fall. So, because that's what happens when you drop something. So we have a special acceleration, the acceleration caused by the force of gravity. And on Earth, it has a special value of 9.8 meters per second squared. Okay? So this is the increment by which the velocity is going to get bigger and bigger. Now, what else is inferred? Well, remember, the ball is dropped. So not only is it in free fall, but its initial velocity is 0. When the man lets go, or whoever lets go, it has to begin moving. So it starts from rest. Okay? Now, last thing, what are we trying to find? We're trying to find V sub f. How fast is it moving when it strikes the ground? Okay? Notice, no time is known. Okay, so that means the alternate equation if we don't know the time. And since we're finding VF, I'm going to write it in this form so it's on the left side already, because I know you guys like to have your unknowns on the left side. Me, I don't care if they're on the left or the right. But you guys seem to be kind of picky about that. So we're going to write it like this so it's on the left already. Now, if the initial velocity is 0, that drops out. And we got to do something about that square. We're not asked to find the square of the final velocity. We're asked to find the final velocity. So we're going to have to square root this side, which means we got to square root that side. So we get VF equals the square root of 2AD. All right, now we can plug and chug. So we get 2 times 9.8 meters per second squared times, there it is, 15 meters. All right, if you guys stick that into your calculators, by the way, notice, meters times meters is meters squared. So we're going to get units of meters squared over meters squared, but then we're taking the square root. So that means our units are going to be meters per second, which is the correct units for velocity or speed. So just put this in your calculator and we'll get units of meters per second. I got 17.1 meters per second. Double check me. Not bad, huh? One more. This one's going to be fun. We're going to go to the moon. Let's take the same ball to the moon and drop it from the same height, but on the moon. Okay, we know it's going to hit the ground sooner or later, and it's going to be traveling 7 meters per second when it does. We want to know what is the acceleration due to gravity on the moon. All right, so here we're given that the distance it falls is 15 meters again, and the final velocity when it hits the ground is only, instead of 17.1, it's 7 meters per second on the moon. Not as fast, is it? Okay, inferred information. Inferred is the fact that we drop it so it starts from rest. Okay, what are we trying to find? We're trying to find the acceleration due to gravity on the moon. Okay, the acceleration due to gravity on the moon. All right, so let's start off. No time is known. So we're going to use the alternate equation again. So we want to find the G. Initial velocity is 0, that drops out. Now, we don't take the square root this time because this is okay. We know what it is. We're trying to find this. So we want to get rid of the 2 and the D. So we divide them to the other side. So we get VF squared over 2D. See? All right, so we get 7 meters per second quantity squared over 2 times 15 meters. Okay? And meter squared over meters, this meter will cancel on the bottom. So that'll leave us with meters per second squared on the top. So we get 49 over 30. And 49 over 30 would be 1.63 meters per second squared. Whoa, so instead of increasing velocity by 9.8 every second, On the moon, you would only increase velocity by 1.63 meters per second each second when you fall. I call it slow-mo acceleration. Cool, huh? Okay, so there you go. That is the acceleration we will always use for the moon, 1.63 meters per second squared. 1/6 of what it is on Earth. Okay? All right, guys, hope you enjoyed it. We'll be applying this. Have a good day.